Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of the double and half angle identity videos. It is actually probably done for most colleges at maybe a pre-calculus level rather than a trig level, but I like to treat this in a trigonometry course because it is a kind of an important topic. Well, I shouldn't say important, but you do actually run into these formulas in calculus. So let's talk about the product of sum and sum to product formulas. I do want to mention right at the get-go that none of these are memorizable. They're all just going to likely be handed to you if it was on an exam. Now, I can't speak for every instructor, but I don't know very many, I don't know any instructors or professors that actually require their students to memorize these. It's enough to know that they exist, that if you have a product of two trig functions, specifically a sine and a cosine, that you can rewrite them as a sum or a difference. So the product of a sine and a cosine, or a cosine and a sine, or, vice versa. And in fact, some of these are really kind of silly to have memorized anyway, because if you think about it, like the product of a sine and a cosine, it's the same as the product of a cosine and a sine. Multiplication is commutative. So these should be condensed in most textbooks don't have them condensed, but they should be condensed, honestly. Anyhow, so let's go ahead and go about proving just one of them. It doesn't really matter which one. In fact, let's take a gamble and just showcase how a proof of any of these works. And I'm not going to tell you which one we're proving. The way they all work is, let's suppose that you want to prove, I don't know, let's say you want to prove this third one. Okay. So what you would do is you would write down the expansion for the cosine of the sum of angles and the cosine of the difference of angles formula. So I'll just say cosine of the sum of angles. Well, that's equal to the cosine of the first angle times the cosine of the second angle. And then minus, because it's always of the opposite sign with the cosine of the sum of angles, that is, minus the sine of the first angle, the sine of the second angle. All right. And if you had the cosine of the difference of the two angles, well, it would pretty much be the same formula, but with a plus. Now, remember what we're trying to prove. I said, let's go ahead and prove this third one. And to prove the third one, you would just add together those two formulas for the sum and difference of angles for the cosine. So I'll just take those two formulas and add them up. Let me just do this, add them up. And on the left-hand side, you will get the desired cosine of A plus B plus the cosine of A minus B. And on the right-hand side, well, the sines, they'll cancel beautifully, and you'll just have two of these cosine of A, cosine of B's. And then dividing both sides by 2, you'll get the desired result, that the cosine of A times the cosine of B is equal to 1/2 the sum of the cosine of the sum of the two angles and the cosine of the difference of the two angles. And all of the proofs go along a similar fashion as that first proof there. So there's no need to go through and prove all of them. They all kind of go the same way. In fact, this is a great way to justify that you shouldn't bother memorizing these anyway, because if you happen to know the sum and difference formulas for the sine and the cosine, you could just quickly add or subtract their sums or differences to derive these formulas if you really need to. The sum to product formulas actually are derived from using the product to sum formulas. So let me go ahead, we'll prove this one only, because, well, we just proved its sister in the other page. So recall that was what we just proved. Notice that I'm using different lettering here. I'm not using capitals. That's for a very specific reason. We're going to make a substitution here. The substitution we're going to make is, well, let's see. I would like this argument here to be the a plus b over 2, capitals. So what we're going to do is we're going to let little a equal capital A plus capital B over 2, and little b, we're gonna, whoops, that's supposed to be a little b, sorry about that. But we'll let little b equal a minus b, capital A minus capital B over 2. And that's because of what I see in this theorem right here. I just want to trade out those arguments for the capital A plus capital B over 2 and the capital A minus capital B over 2. Of course, if you multiply both sides of this by 2, you'll get 2 times those, the cosines of those. So let's go ahead and do this. This would imply that we have the cosine of, well, little a is capital A plus capital B over 2, plus little b is capital A minus capital B over 2, plus cosine of, again, little a is capital A plus capital B over 2, and then minus little b, which is capital A minus capital B over 2, and then this is equal to twice, because we're multiplying by 2 here, the cosine of capital A plus B, and so on and so forth. So I'm just going to fill this in very quickly. Capital A plus capital B over 2, and cosine of capital A minus capital B over 2. Sorry, that parenthesis should have been elsewhere. There we go. All right, so we get down to that point, and then if you notice here, the argument of the first cosine, you'll have 2a over 2, or just capital A. That's what that reduces down to. So the cosine of capital A plus, and then the second one, you'll have a over 2 minus a over 2. Those cancel. You'll have b over 2 minus a negative b over 2, which is 2b over 2, which is b. So that'd be the cosine of capital B. And this is equal to, again, twice the cosine of the sum, I should say the average, it's probably a better way of saying that, of those angles, times the cosine of their distance over 2. All right, so that's how you prove any of them. You just make that substitution. Not a big deal. Again, these formulas are not memorizable, but they're useful to know that it's useful to know that they exist. So when you're dealing with the product to sum and sum to product formulas in general, when you first learn them, there's just a lot of rewrite this product as a sum or rewrite this sum as a product. So I'm just doing a couple of those examples first. So here's a product. We're being asked to write this as a sum. 11 sine of x over 2 times the cosine of x over 4. Now, if we were to turn the page back to our product to sum formulas, we would see that the sine of A times the cosine of B is the same as 1/2 times the quantity, the sine of the sum of the angles, so sine of A plus B, and then plus the sine of the difference of the angles, sine of A minus B. And so we're just going to insert into this formula x over 2 and x over 4 for A and B. So this, in this case, we're just going to say let A equal x over 2 and B equal x over 4. I'm not a huge fan of following formulaic recipes, but the reality is that's what you're going to do here. So there's just no way around it. So 11 sine of x over 2 times the cosine of x over 4. This is mostly a plug and chug style problem. It's 11/2 times the quantity sine of the sum of those two angles, x over 2 plus x over 4, divided by 2. So let me divide that by 2. And then, oh, nope, it's not divided by 2. I don't know why I wrote that. It's because we just finished the other formula. Sorry. So it's x over, just the sum of the angles, x over 2 plus x over 4, plus the sine of the difference of the angles, x over 2 minus x over 4. You're going to use a lot of the even odd identities when you're simplifying this stuff. So you get 11 halves times the quantity. Well, in this case, let's see, that's 2 fourths plus 1 fourth. That's 3 over 4, sine of 3 over 4, sorry. So sine of 3 over 4x, and plus the sine of, let's see, 2 over 4 minus 1 over 4 is 1 over 4x. Now, I did say that you will often use the even odd identities with this stuff. It's because of that difference of angles. You will often get a negative angle there. We didn't in this case, but you often will. And that's okay, because if there was a negative there, we know sine is odd, and so we would move that negative to the outside of the sine function. But we did not get a negative there, so I'm not going to bother with that. This is that product written as a sum. You could leave the 11 halves on the outside or distribute it. It really doesn't matter. Here is that same style of typical problem where we want to write the sum, or in this case, the difference, as a product. And we're just going to steal the formula that the cosine of, let's see, A, sorry, I have to look at these because I don't have them memorized either, minus the cosine of B is equal to, in this case, it's going to be a negative 2 sine of the average of the angles, so A plus B over 2, times the sine of A minus B over 2. So we're going to go ahead and do that. In this case, we have the cosine of 4x minus the cosine of 6x, and that will equal a negative 2 sine of 4x plus 6x. So you can just see it's, again, another plug and chug style problem. Sine of 4x minus 6x over 2. And then simplify this out, right? So negative 2 sine of, let's see, that's 10x over 2, which is 5x. And this is sine of negative 2x over 2, which is a negative x. And again, as I mentioned in the previous problem, you will often run into these even odd identities. Sine of negative x is negative sine of x. We have a negative out front, they cancel, so you get 2 sine of 5x sine of x. I'm trying to say whether or not this is awesomely important. I don't know. It's okay. It's useful in proofs, actually. And in fact, I have a really good proof coming up here. This guy right here, I searched around for a really good proof for a video, and I thought, man, this is a really good one. I like this one a lot, just because of the way it looks. You have the sum of the sine of x, and then the sine of 2x, and then the sine of 3x, all the way up to sine of 5x. It's the same thing with the cosines, but in the denominator. And that ratio should be the tangent of 3x. Proving this looks to be pretty daunting. I actually haven't done the entire proof, but I think that it would be somewhat easy to do if you use the sum to product formulas, because you want to turn this sum into a single term. So hopefully if you turn it into a product, things will cancel, is what I'm thinking. So let's go ahead and start in the numerator. We'll take the sine of x plus the sine of 2x, and we'll use the formula. In fact, I'll write them up above because I want the room down below. Again, I have not proved this, so I would like to reserve some space just in case I need lengthy space. Sine of A plus sine of B, just to remind us, is 2 times the sine of A plus B over 2 times the cosine of A minus B over 2. And then in the denominators we'll be using, or in the denominator, we'll be using the sum of cosines formula, which I've written out there. And so let's go ahead and start. The left-hand side is what we're going to be working on. And, you know, I always use green for the left-hand side. Let's go ahead and do that. Left-hand side is equal to, let's see, the numerator. Sine of x plus sine of 2x. Using the formula above, that's going to be 2 sine of x plus 2x, which is 3x over 2, times the cosine of x minus 2x, which is a negative x, over 2. I'm going to go ahead and just rewrite the sine of 3x, because the first term is the sine of x plus 2x. And then I'm going to go ahead and just take advantage of space and time here to go ahead and add these two together. So adding those two together, I would get, let's see, plus 2 sine of, let's see, that's going to be 4x plus 5x over 2. So that's 9x over 2. And cosine of the difference of those angles, so 4x minus 5x, which is a negative x, over 2. All right. So that's what the numerator compresses to so far. We're not done, but that's what it comes to now. Now we're going to do the same thing in the denominator. So in the denominator, we'll go ahead and add up the cosine of x and the cosine of 2x using the formula right here. So cosine of x plus the cosine of 2x is going to be twice the cosine of x plus 2x, which is 3x over 2, and times the cosine of x minus 2x, which is a cosine of negative x, over 2. I will again just rewrite that cosine of 3x in the center. And my choice to do that is because we want to end with a tangent of 3x. So I'm hoping that all of our terms have an angle of 3x in common when we're done. All right, let's see, plus. And now what I'm going to do is go ahead and glue together these two, the cosine of 4x, cosine of 5x. Let's see here. That'll be twice, using the formula up above, cosine of 9x. Is that right? Yeah, 9x over 2. And times the cosine of a negative x over 2. That's 4x minus 5x is the cosine of negative x over 2. All right, so we get down to there. And you take a look at that, and it does not look like it's really going to super work out. But what I'm going to do here, let's see. I'm going to combine some terms. Well, not combine them, but group them slightly differently. So what I'm going to do is take this first term and this third term in the numerator, and I'm going to group them together and factor out a cosine of a negative x over 2. Just because I'm thinking that might be a good idea. And a 2 as well, in fact. And same thing, I'll do that downstairs here. I'll group those two terms together and factor out a cosine of x minus, a negative x over 2. And by the way, the negatives, because cosine's an even function, you can get rid of the negativity on that cosine as well. So let me go ahead and do that. In fact, maybe I'll take my time with it. So all I did here was I just moved those third terms forward by just switching positions, that's all. And then I also use the fact that cosine is an even function to say cosine of negative x over 2 is the same thing as cosine of x over 2. So that's all I did here. Now the next step I'm going to do is go ahead and factor out of each of those first two terms a 2 and a cosine of x over 2. And we get down to this point right here. Something I want to mention as I was writing this out, I kind of thought, this reminds me of what some students will do. They'll make a tragic mistake where they will break this fraction apart and they'll say, oh, well, this last piece right here, that's a tangent of 3x. That is not true. That is totally not true. That last piece right there, you cannot break apart a fraction like that. So do not do this. Don't say a plus b over c plus d. That is not the same as a over c plus b over d. Don't do that move. Don't break those apart. So the reason why I'm saying that is because I will get students who somehow make it into transfer level mathematics and still make those styles of mistakes. You should not do that. I also have students that love to do this. Oh, these 2's will cancel, and so will these cosines. Nope, they will not, because factors cancel, not terms. And in that numerator, you have 2 terms. The first term, this whole thing right here, and the second term. And because you have 2 terms, if you're going to cancel anything, it has to be common to both of those terms. And unfortunately, Nothing is common to both those terms, at least right now. So let's go ahead and move forward. This is just a bit of a warning because I have seen people do that. So I'm going to use those sum of sines and sums of cosines formulas on this stuff right here. So we're going to add up the sine of 3x over 2 and the sine of 9x over 2 into a product. I think that's a good idea. All right, so let's do it. So this is going to equal, whoops. We have the 2 cosine of x over 2 in that numerator. And now the sine of 3x over 2 plus the sine of 9x over 2 is going to turn into twice the sine of the sum of 3x over 2 and 9x over 2 divided by 2 times the cosine of the difference of 3x over 2 and 9x over 2 being divided by 2. Right, I'm just double checking with my formula on the side because, again, these are not things that I memorize. Plus the sine of 3x is hanging off the back end there. Divided by, and you do the same thing, 2 cosine of x over 2. The cosine of the sum, or the sum of 2 cosines, will turn into twice the cosine of 3x over 2 plus 9x over 2 divided by 2. So basically the sum of their angles divided by 2. And then the cosine of the difference of their angles divided by 2. So 3x over 2 minus 9x over 2 divided by 2. All right. And then we still have that plus cosine of 3x hanging off the back there. Remember, our ultimate goal is to get to a tangent of 3x. We're not there yet. What does this turn into? So let's see. We have 4 in the numerator here. We have a cosine of x over 2. We have a sine of, let's see, 3x plus 9x. That's going to be a 12x. Divide that by 2. That's a 6x. Divide that by 2. It's a 3x. Times a cosine of, let's see, 3x minus 9x is a negative 6x. Divide that by 2. It's a negative 3x. Oh, okay. I guess that's it. Negative 3x. Let me just double check that. Negative 6, negative 3. Yeah, negative 3x over 2. Not 100% sure if that's going to work out, but at least we get there, right? Plus sine of 3x. In the denominator, we have, again, 2 times 2 is 4. Cosine of x over 2. And then, let's see, cosine of 3x plus 9x, 12x divided by 2 is 6x, divided by 2 is 3x. Cosine of the same thing, which is a negative 3x over 2. Plus sine of, cosine 3x. Now, I can easily see that both terms in the numerator have a sine of 3x in common, and both terms in the denominator have a cosine of 3x in common. So I'm going to factor those out of this statement. In the numerator, factoring out the sine of 3x, I'm left with a 4 cosine of x over 2, cosine of 3x over 2, because cosine is even, I don't have to worry about that negative, and then plus 1. In the denominator, I get cosine of 3x times that very same factor. And those two factors, because they're identical, will cancel beautifully. Notice how I can cancel factors, right? Now you see between numerator and denominator, it's just the product of some factors, so you can cancel factors. And we get to the sine of 3x over the cosine of 3x, which is a tangent of 3x, where we want to arrive. That's a pretty fun proof. And while that is all I have for this video, I just want to make sure you understand that as you're working through problems in trigonometry and pre-calculus, that if you do have a sum or a difference of sines or cosines, then you can always use these sum to product formulas if you have them on hand. And it only works, again, if you have a sum of sines or a difference of sines, or a sum of cosines or a difference of cosines. If you have a sum or a difference of both the sines and cosines, so let's say sine of x minus cosine of y or something like that, you could use the compression formula, which is basically a formula for compressing a sum or a difference of a sine and cosine into just a regular old sine. And I have a different video on that. So and I think it's like maybe 2 or 3 videos prior to this. So you're welcome to watch that if you need it. Otherwise, you guys have a good day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.